Hello everyone, my name is Chen from the University of Edinburgh. I'm presenting my work on biomechanics-informed neural networks for myocardial motion tracking in MRI, which was done at Imperial College London. Myocardial motion tracking is one of the crucial steps for the dynamic exploration of the heart, which enables the accurate quantification of the regional function measures. Motion tracking can be commonly addressed by the image registration techniques. Image registration is an ill-posed inverse problem where there exist many possible solutions to register between images. To ensure the deformation to be unique and physiologically plausible, regularization techniques are often employed to convert the ill-posed problem to a well-posed one. Conventionally, regularization is imposed explicitly on the regularization term R, all the feasible transformations D, with some assumptions on the deformation such as the smoothness, invertibility, and volume preservation to achieve some desired properties. Though these assumptions are generic, there is often a lack of application-specific prior knowledge to inform the registration. Since we are aware of the biomechanical models of the heart, could we possibly incorporate such information into this image registration and also to implicitly learn the behavior of these regularizations in a deep learning framework? Inspired by this, here we propose a biomechanics-informed neural network to incorporate the prior knowledge of biomechanics into the image registration. Specifically here, our proposed method mainly consists of three components: a biomechanical simulation based on these equations, a VAE regularizer that can implicitly learn the underlying properties of these biomechanical simulations, and a registration network that can generate biomechanically plausible deformations. So now let's have a look at each of these components in detail. First, we propose to generate a set of deformations based on these biomechanical simulations. From the perspective of solid mechanics, it can be considered as a plane strain problem with these governing equations. Here, the first equation describes the equilibrium within an elastic body. To solve the deformation, a constitutive law is provided which assumes a hyperelastic material behavior. In the simulation process, given a segmentation mask at ED frame, an artificial pressure can be applied to match the ventricle area of the ES frame. So the pressure value can be determined via the inverse finite element method. And by uniform sampling the pressure value, we can then generate a series of these deformation fields. Once we have these biomechanical simulations, we can learn the prior knowledge of biomechanics. Here in particular, we leverage the variational autoencoder to learn the probability distribution of these biomechanical simulations and to use it as a learning-based regularization. So the VAE is trained by reconstructing the first-order derivative of the deformation fields, that is the delta phi here. And the PZ denotes the prior Gaussian distribution with the Z as the latent vector that's encoded by the VAE. Here we have a hyperparameter beta that controls the trade-off between the reconstruction quality and the extent of the latent space regularity. To inform the registration network with biomechanical informations, here we propose to integrate the VAE regularizer to the image registration network. This aims to regularize the deformations to fall on the manifold that is represented by the latent space of VAE so that it can generate biomechanically plausible deformations. And this is also advantageous over explicit regularization terms, as such data-driven approaches can implicitly capture the realistic and complex motion properties from the observational data that can't be explicitly specified. The final objective function to train this registration network can be formulated as this, which consists of an image similarity measure and the VAE regularization. Here, a hyperparameter alpha is introduced to trade off between the similarity and the physical plausibility of the deformations. The architecture for the registration network was adopted from one of our previous approaches, which has shown to be effective for the myocardial motion tracking. In experiments, we used 300 short axis cardiac senior MRI sequences from the UK Biobank dataset, and we split them into the training, validation, and testing. For biomechanical simulations, a separate dataset of 200 subjects in UK Biobank dataset was also used. Additionally, the ACDC dataset was employed for the generalization study. The segmentation masks used in this experiment were all obtained via automated deep learning method. Firstly, we investigated the effect of this VAE regularization. Here, we varied the value of alpha and investigated its effect on 3 different measures. It can be observed that as alpha increases, the change of myocardial volume is reduced, which means better volume preservation, and the observational radial and circumferential strain are more reasonable and within the range that has been reported in previous literatures. However, this is at the expense of the decrease of the registration accuracy in terms of the dice. Since the motion estimation was performed on stacks of 2D slices, the incompressibility of the myocardium can't be guaranteed due to the out-of-plane motion. However, these results should still be able to indicate that the proposed method has the potential and ability to implicitly capture these biomechanical properties. Furthermore, we compare the proposed method against some of the state-of-the-art approaches such as the freeform deformation with volume preservation, the diffeomorphic demons, and the deep learning with the smoothness penalty. We first compare them in terms of the registration accuracy and the volume preservations. Here, it can be observed that when the volume preservation are in a similar range, our proposed method can achieve a better registration accuracy, especially on more challenging slices. And then we compare these approaches in terms of the peak, radial, and circumferential myocardial strain. To better understand the strains, here we compare the results from the cardiac senior MRI with that from the tagged MRI, which has been used as a reference modality for the strain analysis. Here we can see that our proposed method can achieve the radial and circumferential strain in a more reasonable value range that is defined by the reference. Besides, we also visualize the displacement and its log of Jacobian determinant across one cardiac cycle. The proposed approach shows better volume preservations at different cardiac phases. So these results indicate that incorporating biomechanical prior knowledge can benefit the motion tracking, and the learning-based regularization function is also able to implicitly capture and represent biomechanically realistic motions. In addition, we performed a generalization study by deploying the model trained on UK Biobank to the ACDC dataset. Here, compared with the baseline deep learning approaches, the proposed method can generalize well to the unseen domain with a better registration accuracy. This is likely due to the benefit of these biomechanical regularizations, which enforces the generated deformation fields to be biomechanically plausible and thus less sensitive to domain shift. To conclude, we have presented a novel biomechanics-informed neural network for image registration with an application on myocardial motion tracking in cardiac senior MRI. We have also shown that the proposed VAE-based regularizer is able to effectively exploit the biomechanical prior knowledge and to inform the registration network to generate biomechanically plausible deformations. Our results indicate that the proposed method can achieve better registration accuracy with the realistic motions and also have a better generalizability to unseen domains. Here, I'd like to thank all my co-authors for their contributions in this work. The code for this work is also publicly available on GitHub. If you are interested in our work, please come to our oral session on 7th of October at Image Registration C. I'm also happy to discuss with you at the poster session. Thank you.